I don't know why today was so difficult. I know I just burned 3 minutes, but it felt like forever. Okay, so we left off on, and again, this is gonna be a day where we kind of switch back and forth a lot. Sorry, Zoom people, and of course I have this backwards from taking screenshots last night. Where's the button I need? There it is. It is really hard working the screen that is a projector. There we go. And then, okay. So we had left off here. Right, we were talking about the mechanism of an olefin metathesis. We had walked through it, and then I think we'd gotten to this being our where we had stopped. So, right, you do a 2+2 to load your olefin onto the ruthenium. That's the first step, and then that ruthenium that has your olefin loaded onto it then goes through a catalytic cycle where it reacts with your other double bond. Does a 2+2, retro 2+2 to put those two double bonds together to give you the product, plus ruthenium that just has a CH2 on the end, and that reacts with another the first double bond again to give you the ruthenium with a double bond on it. And I think I ended on the fact that these reactions, I showed you, this shows one path that leads to product. But in actuality, this reaction happens a bunch, and a lot of times the pathway that it goes down is non-productive. It doesn't lead to the product that you want. And it just keeps doing the reaction over and over and over again until it funnels off to the most stable thing that is made in the reaction. So if your product is not particularly stable, it's not going to be formed in high amounts, because the way that olefin metathesis works is if it makes a double bond that's not stable and it can react with again, it will. And it'll just keep chewing those products up until it ends up with whatever is the lowest energy thing it can make. So there are two types of olefin metathesis. There's cross metathesis. And cross metathesis is where two different double bonds get put together. And this is kind of what we had done in a lot in Organic 1, where, and that's kind of the base thing that we had shown initially, where you have, right, you have two double bonds, let's say this and this, and then you have your catalyst, and you end up putting those together. And it's inside double bond of one double bond ends up bonded to inside double bond of another. And the byproduct that you make during this is you make ethylene, which is a gas that will just bubble out of your reaction. Right, so you take two double bonds and you put them together to make one new molecule, plus ethylene as a byproduct. Right. The other type of metathesis is a ring closing metathesis. Here you have two double bonds in a single molecule, and you use the olefin metathesis to close a ring. So you have two double bonds at opposite ends of the molecule. Metathesis will close that ring down. So this is kind of what we showed, or what I showed in the synthesis example that I had previously, right? Where in my molecule, right, we had, this is going to be ugly, let me fix it. And this is also really big for some reason. Good job, me. Right, we'll leave the rest of it off. Right, but then we close this carbon, make a bond from this carbon to this carbon, and you end up making a ring. A very small ring in comparison with the very large one I initially drew. Right, and so you have blue carbon and red carbon. Right, and here your byproduct is right this carbon right here, this carbon here, this carbon is that. So sorry, this is a little fugly, a lot fugly, but what are you gonna do? So here you're taking a molecule that has two double bonds, you put those double bonds together and you form a ring. Give it. Oh god, I'm sorry. It is for the drum right there. Sure, come on. Reasonable. So those are, other than the fact that it's poorly drawn, reasonable. So those are our two types of metathesis. Take two molecules and stick them together. Take one molecule and close a ring. All right. Next slide. So, here's a bunch of different examples of cross metathesis reactions. None of them are like super duper interesting in terms of structure, but what is interesting about this is the E to Z double bond ratios. So if you look down the side, I'm having a hard time reading off the screen. Right at the top, you have 20 to 1, right? And then if you change the methyl group on that ketone to a hydrogen, your E to Z ratio falls to basically 1 to 1, slightly above 1 to 1. Right, so just that small change in sterics changes how much you want to make the double bond E, or you want to make the double bond trans, right? Then you move that methyl group over, so it's on the double bond. Now your E to Z ratio goes back up to 20 to 1. Right? You change that, you make it an acetal, which is probably a little bit bigger. It's 3 to 1. Move the double bond to the other side, and you start with an internal double bond. It's 2.5. So just small changes in sterics and the size of the groups changes your selectivity, and that goes to the fact that this E to Z is always determined by thermodynamics, how stable the product is. So when you have a 20 to 1 E to Z ratio, the E product is way more stable than the Z. So as the metathesis catalyst makes products, whenever it makes the Z, whenever it makes a cis double bond, that is able to react with that, and it will react with it again until it makes an E double bond that's really stable, and then that just kind of falls out of the reaction and doesn't get reacted with again. Right, so this is, remember in organic, we talked about kinetic versus thermodynamic control, where thermodynamic control, you go back and forth, you set up an equilibrium until you make the most stable thing you can, and then that thing stops reacting. That's what we're doing here, is we go back and forth, until we make the most stable thing that we can. When the E to Z ratio is close together, there's not a big energy difference between E and Z, so it just keeps making those, it just makes a mixture of those products. So you can change the sterics, you can change where the groups are, and basically shift how stable E and Z are. So this isn't so much, it's not so much you can like always predict, but you can always make a pretty good assumption that the E double bond is going to be more stable. So a regular Grubbs catalyst is going to favor making the trans double bond, making the E, because it's going to be more stable. But it's hard to know exactly what that ratio is going to be. Is it going to be 3 to 1 or 20 to 1? It's usually something you have to like just actually do the reaction and tinker with the reaction conditions to maybe get it to favor the product you want a little bit more. There are in recent years versions of the Grubbs catalyst that specifically select for E double bonds. They change the ligands, and they can make it make Z double bonds. So they can make it make cis double bonds, but they've changed the ligands and stuff to like kind of force it in that direction. We're not going to go super into the weeds on that. Ow. So I forget what this molecule was for, right? But here's an example of a cross metathesis where they use beta Grubbs. They get a really good E to Z ratio, and they're able to do this simple cross metathesis. So, behind the scenes, all of these ones that are on weird white backgrounds are because this got drawn years ago, and I couldn't make it a ChemDraw file anymore. But these were drawn more recently. So here's some examples of ring closing metathesis that are actually been used in synthesis. So, right, they have this really big molecule. Oh, I forgot a double bond. Crap. There's a double bond. Can't really point to it. Beside the epoxide, should be a double bond there. People in Zoom can't see me jump. Should be a double bond there. So they do a ring closing metathesis. They take the double bond that is beside the epoxide and the double bond that has the methyl group on the end. Those react and close to make that ring. And again, there should be a double bond there. And then another example, they take those two double bonds and close it and make a 7-membered ring. The same kind of rules from like organic 1, where like 5 and 6-membered rings are easy to make. And then smaller rings like 4-membered rings and large rings like 7 and 8s are hard to make. Still hold true for metathesis. So a lot of times when you see these examples, they might actually have like a concentration associated with them. So it might be like this top one, I don't remember exactly, but it might have like 0.005 molar, meaning that they ran the reaction at a very dilute concentration so that the two molecules never saw each other to do a cross metathesis. So you run the reaction at a really low concentration so that when the catalyst loads onto the double bond, the only other double bonds it's going to see are the double bond in the molecule that you want it to react with. So you can control if it's going to do a cross metathesis. Cross metatheses want to be at higher concentrations, right? So you have two molecules bump into each other. Ring closing metatheses want to be at lower concentrations so that you never have two molecules bump into each other. If that makes sense. Right. So like this right here has the 0.005 molar. If they ran it at a higher concentration, they got cross metathesis, where they took two of these molecules and stuck them together. Right? So they ran it at a really low concentration so that they got the ring closing metathesis. I guess the normal, a normal organic reaction is run somewhere between 0.1 and 0.2 molar. Is just kind of the default concentration. So 0.005 is significantly less concentrated than a normal reaction. Here is this neat, next is kind of a neat dimerization. So they use the Schrott catalyst, and they're able to get a cross metathesis and then a ring closing metathesis. So they stick the two molecules together in a cross metathesis, and then they close this double bond, right? They make this one in a cross metathesis, then they close the other side in a ring closing metathesis. So they're able to stick those two groups together in one step. So far, so good? Reasonable? All right. So, big picture takeaways. Right? Metals are used in synthesis rather frequently. Right? We covered lithium halogen exchange reactions, palladium catalyzed reactions, and the big thing there is all your palladium always goes from palladium 0 to palladium 2, does some stuff, it goes back to being palladium 0. And then olefin metathesis, you take two double bonds and you stick them together. The big broad strokes. So, that is metals. Metals I thought were important enough to use in graduate school, / had to use in graduate school, that you now know about. I wanted to do, so a lot of this stuff is, a lot of stuff we just talked about involves double bonds, right? And I wanted to go over how you can make double bonds, right? In kind of different ways than, hey Zoom, come back Zoom. 1 second. Zoom abandoned me. Not the Zoom people, but just the Zoom program. So Zoom program. Let me do this. I'm gonna just share a random screen with you guys for a second, and then that should fix it. Because I'm super good at technology. Hey, we did it. Okay. So I'm going to go over a bunch of ways to make double bonds. So some of this is rehashing some of the stuff we did in Organic 2, right? Where we go into a little more depth on Wittig reactions. Then some things are just Wittig variants. And then there are some olefinations that are completely and totally kind of different from what we had done, what you've seen previously. So I couldn't find one synthesis that I could just keep going back to for examples of olefinations. But I did find a molecule that had a bunch of different syntheses that used different types of olefinations to use that to illustrate. So I wanted to kind of introduce the molecule that you're going to see multiple times. And did that not get fixed? I thought I fixed that. 1 second. He's going to fix it. We're going to do it live. As long as ChemDraw will open, we'll fix it. So, the molecule, if I get to it, is called discodermalide. And I could have swore I fixed this, but maybe I missed it. I hope it's not screwed up somewhere else. That's right though. If it is, we'll fix it then too. So discodermalide has an interesting history. Again, let's see if you want to work Zoom. Again, share random screen. I know, this is riveting stuff. Me struggling with technology. Okay. All right. Boom. Okay. So this is discodermalide. So it was discovered in 1990. I think it's from a sponge, or it was from a marine product. And it was found to be a microtubulin stabilizing agent. So here we go, biology time. This is something that they secretly don't tell you when you're a grad student in biology, in chemistry. You have to understand the biology too, which I never thought was fair, because all the biology people I ever dealt with never knew any of the chemistry, but I was supposed to be able to explain how all the biology worked. So when cancer cells or any cell divides, right, it has to build kind of a framework, or like almost like a skeleton of microtubules that help during mitosis to help split the cell apart. And that framework of microtubules has to then break down for the cells to finish splitting. Right? So for mitosis to be completed, you have to break your microtubules down. And microtubules have weird kinetics and dynamics, right? When they're building up, they're like building faster than they fall apart. And then when they break down, they're breaking down. They're still building, but they're falling apart faster than they build, right? So there's a bunch of anti-cancer compounds that interact with microtubules. They are either microtubule destabilizing agents that make it so that microtubulin falls apart and you never get to split the cell. Right? The cell doesn't get to go into mitosis because as it starts to divide, the microtubulin doesn't form. Then it gets too many chromosomes or too many, and then the cell goes like, oh wait, I'm broken now, and kills itself. Right? Or there's discodermalide, which is a microtubulin stabilizing reagent. So it will go bind to microtubulin, make it so it can't fall apart. So you get a cell that is divided, but doesn't get to fully split. So it has two nuclei and then goes, oh wait, I'm not getting to split. I have to go into apoptosis and die. Right? So at the time this was being developed or being looked at, there is a compound called Taxol. It's called paclitaxel is the commercial name for it. And it is a commercially used, a clinically used anti-cancer compound. And it works by stabilizing microtubule. So these compounds, like all chemotherapeutics, are not very selective. So if you give chemotherapeutic to someone, the reason that they get sick, their hair falls out, and things like that is because you are killing. The compounds work by basically interacting with quickly dividing cells. So if a cell's not dividing quickly, it doesn't matter that its microtubulin is messed up. But if a cell divides quickly, like cancer cells, then you get a bunch of those cells that get trapped in mitosis and don't get to go through the rest of the cell cycle. Right? So you give someone Taxol and their hair falls out is because the hair cells are quickly dividing cells. So you end up doing more damage to those cells than you do to like skin cells that don't divide as quickly. So discodermalide is 1,000 times more potent as a microtubulin stabilizing reagent than Taxol that was already clinically proven to work. So there was a lot of focus on, hey, we know this mode of action of binding to microtubulin and making it so it's stable and doesn't fall apart is a really good pathway. It has been shown to work clinically. And here's this compound that's way better at that. This seems like it's a good candidate to be an anti-cancer compound. So it was looked at by a lot of different research groups. Total synthesis was pursued, the development of drugs. There were studies on just exactly how the compound worked, exactly where it was binding on microtubulin to stabilize it. So there's a big push in the late 90s, early 2000s to look at this compound and try to develop it further. So the IC50 was in the low nanomolar range across a bunch of different cell lines. So does anyone know what IC50 stands for? Have you heard the term LD50? So IC50 is inhibitory concentration, 50%. So it is the concentration required to inhibit cell growth to 50%. So basically to cut it in half. LD50 is lethal dose that kills 50% of the population. So LD50, so that 50 is telling you what percentage you're knocking it down. So this is growth inhibition or inhibitory concentration to like stop the cancer growth, to get it to 50% against the control. So things that are usually you'll start looking at drugs in like the micromolar range of activity, and you're like, okay, this is fine, right? This is a place to start, and try to get it to low micromolar. Nanomolar is extremely potent. Like, you don't need hardly any compound to get to those levels of concentration in the body. Right? So it's really exciting, to the point that Novartis actually scaled up an academic synthesis and was making like multi-gram quantities. So that column you guys ran in lab, I guess 2 weeks ago now, they were running columns that were 60 feet long. They just had like a warehouse with silica and a column in it, because they were taking a synthesis that was done like in an academic lab and then scaling it up to industrial scales, because they couldn't figure out a better process. So they just used the process that was in the literature. And they could go so many steps. And then they were like, oh man, we have to run a column on this. And so, because it was so promising, it was one of those things where they're like, we can make so much money if this works. We're willing to spend tens of thousands of dollars to try to purify this thing. So it made it into clinical trials, but unfortunately, it was not. It was not a good drug candidate. There's just kind of too much going on, too many places for it to get oxidized in the body to like break apart and just not end up working or being toxic. I do believe it ended up being really toxic. So, but this was like the thing du jour in the early 90s. Sorry, late 90s, early 2000s. This was just the molecule to like work on. So, I'm going to talk about about transition states when I talk about Wittig reactions. And I just wanted to give you a quick reminder of what transition states are, and then we can talk about the types of transition states. So remember, transition states are on a reaction coordinate diagram, the peak between points on a reaction coordinate diagram. So, all right, remember, you've got your reaction coordinate diagram. You have energy on your y-axis, and you have reaction progress on the x-axis, right? And you have starting materials over here, and you have your product over here. In the peak, this is poorly drawn. This is your transition state. Right, that is the point of highest energy in this, where you have partially formed bonds. Remember, transition states aren't something that we can actually observe. They're just something that makes sense, that has to be there for the reaction to make sense how it happens. So these are high energy, they're fleeting, they're not around very long, and they have partially formed bonds, right? So you have your transition states. There can be multiple transition states in a reaction, right? So you can be, right, these are the peaks are your transition states. Right, in between here, this is an intermediate. Right, so transition states are between starting materials and intermediates, starting materials and products, or intermediates and products. In between one intermediate to another, you have a multiple step reaction. Right? And there are different types of transition states. That's what I want to talk about. There's something called the Hammett postulate. Right. So this next slide is slightly different than what what I sent out, just because I wanted to add the Hammett postulate stuff after the fact. Right. So the Hammett postulate compares the energy of transition states to the starting material or the product. and then says whichever whichever the transition state is closest to an energy, we can use that to model the transition state. So you have early transition states where the reactant is close to energy to the transition state. So we can say that the transition state looks more like the reactants. Right? So we can use interactions that we see in the reactants to model the transition state. Right? So an example of this, so what it kind of would look like, right, is, I'll kind of do the exaggerated version. Here's your starting material. Right, this is an early transition state. Right, because the transition state is close to energy, closer to the energy of the starting material than it is the product. So we can assume that how the two starting materials interact, or how the interactions in the starting material have a greater impact on what that transition state looks like than any interactions you would see in the product, right? Because the product is really far away from, energetically, the transition state, right? And then we have late transition states, right? So a late transition state is you have your starting material, here the transition state is closer in energy to the product. And so we can assume that my product looks more like the transition state than the starting material does. So you can use interactions in your product to help model what you think the transition state is going to look like. So you can use this to try to figure out what interactions in your transition state is going to matter, and then try to use that to predict what products you're going to get out. Right? So if you're like, oh, this is a late transition state, I'm going to make the product that is most stable, because that's going to lessen the interactions in the transition state. Right? Whereas in an early transition state, it's, well, how can these two molecules come together and have the least interactions and make the transition state more stable? And then whatever that is gives me whatever product I get. So it's how do these, in one case, it's how do these come together in the best possible way, is an early transition state. A late transition state is, well, what's the most stable way for my product to look? That's going to be how my transition state looks. So you're just kind of changing your perspective. So there are, and this comes up with Wittig reactions. Okay. So, and then there's like a third type of transition state, which is, call it the cop-out, right? And this is where it's kind of in the middle, where it's kind of maybe equally, like roughly equal in distance and energy from starting material to product. And then those transition states, you can't use your starting material or your product to model them. You're just kind of blind to what that looks like. So we all remember the Wittig reaction from organic 2. It was good times, right? So if you remember, in organic 2, we said Wittig reactions favor the cis double bond, right? I think I told everyone, just draw the cis double bond as the only product. That's really all you make. We need to have an aldehyde and then a Wittig reagent that only has one substituent on it. So basically, this top example that I have up here, this is the like classic Wittig reaction. And you get 16-to-1 cis double bond to trans double bond. Basically, you only get one. If you make the groups beside the aldehyde bigger, you can push that selectivity even further, right? You can push it to 99 to 1, right? Where you basically see none of the trans double bond. Right? Now, if you start to change your Wittig reagent, right, you take off one of the phenyl groups for an ethyl group. Ethyl is significantly smaller than a benzene ring. Right? That skews now your selectivity. Right? Now you're favoring the trans double bond. You increase your sterics on your group again with that smaller ethyl group. You switch the selectivity back to cis, but you're not nearly at the same selectivity. And this last one, if you have what's called a stabilized ylid. So remember, the phosphorus double bonded to a carbon is called an ylid, right? It is, remember, ylids are stabilized, separated charges. So, again, less talk, more draw, old man. Right, these have a resonance structure that look like this. So an ylid just means you have stable separated charges. So I can separate my charges to phosphorus plus and carbon minus on an ylid, and that resonance contributor contributes a lot to the structure. So it spends a lot of its time acting like this. So it's called an ylid because it's stable, having its charges separated. Right? A stabilized ylid has some electron withdrawing group. 99% of the time you see these, they're going to be an ester or a carboxylic acid. You're going to have a C double bond O as your electron withdrawing group. These have some electron withdrawing group, so now the ylid, when you get to negative charge, positive charge, that negative charge has another place it can go for resonance, right? I can take now, these electrons can come down, push up onto the oxygen. I can draw yet another resonance structure. So stabilized ylids have some electron withdrawing group that through resonance can stabilize the negative charge on the carbon. Right? So your phosphorus is positive, your carbon is negative. The stabilized ylid has some group that's going to suck that negative charge up in resonance. When you have a stabilized ylid, the selectivity for Wittig reactions switches. So you go from favoring the Z double bond, you switch to getting pretty much exclusively the Z, you go from the Z to the E. You favor the trans double bond almost exclusively. We get to 15 to 1 trans to cis, right? Just by adding some electron withdrawing group, usually C double bond O of some sort, right? And so, is there a mechanism? Is there a way that this works that we can explain all of these observations? Right. So, I'm going to remind you of the gentle lie that I told you in organic 2. Right? This was the mechanism I showed you in organic 2. Right? It doesn't really explain all the selectivity we just looked at. It doesn't explain all of it. Right? So you add to an aldehyde, you get a negative charge on the oxygen. Negative charge likes positive charge. It attacks the phosphorus. You get an oxyphosphatane, which is this four-membered ring with phosphorus and the oxygen in it. And then you break those bonds. If you remember, it does something like this. Right. So once you get to the oxyphosphatane, these electrons come up, those electrons come down, and that's going to make your double bond plus triphenylphosphine oxide. Right. So where your selectivity is set in this reaction, right? So in theory, right? Your stereochemistry on your oxyphosphatane should translate to the stereochemistry that you see in your product, right? So here, the R group and the methyl group are on the same side. When this unwinds, or does the retro 2 plus 2, if they're on the same side, you'd think they'd end up on the same side of the product. If they're on opposite sides, you would think they would end up on opposite sides of the product, right? Since this is, remember the term concerted paracyclic reaction? Zoom? Okay, Zoom doesn't remember either. Right. That means so concerted means all your bonds are made and broken at the same time. Paracyclic means all your electrons are moving in a circle. Right? So all my electrons are moving in a circle. All my bonds are being made and broken at the same time. If that's the case, then if my groups there's no chance for any of my bonds to rotate, which means if it cis in the starter, in the oxyphosphatane, it cis in the product. If it's trans, it's trans. Not knowing anything else about this, which one of these two looks more stable? Right? A or B? Right? Would you rather have two groups on the same side of the molecule that can bang into each other? Or would you rather have groups on opposite sides of the molecule that don't bang into each other? Right? You'd rather have things on opposite sides, right? This is why you parents bought a minivan. They put like the annoying little brother up front and you in the back so you couldn't hit each other. Right? If you had like a Honda Civic, you just beat each other the whole time side by side. It was miserable. Right? A is the Honda Civic. The R group and the methyl group are just banging into each other. Like, the R group's like, he's touching me, and it's awful, right? B, they're far apart, they don't interact, right? So if you think B is more stable, you're like, oh, well, my selectivity for a Wittig reaction should be a trans double bond, right? Because the more stable oxyphosphatane is B. But we don't see that. We only see the cis double bond for most cases. So there must be some other mechanism that can explain the selectivity that we observe in these reactions. Right? And so the mechanism that gets used, there's kind of two versions of it. I'm going to go through both of them. Is a cycloaddition mechanism where you, instead of having this act like a kind of like a like a Grignard type reaction where like you add to the carbonyl carbon with a carbanion, right? It instead acts more like a Diaz-Alder reaction, where all your electrons are moving at the same time, and you make a ring in a single step. So instead of being add and then add again, all your bonds are moving at the same time. So you do a 2 plus 2 cycloaddition. I'll draw this out for everyone. So you have your R group. This is a Wittig cycloaddition. Right? It's a 2 plus 2 reaction. 2 electrons from each side. So you're going to have your R triphenylphosphine and H. And you're going to have your H and your R. We'll make this methyl. We'll make it like consistent with what we had before. Right? You can see that these electrons would go here, and these would go there. And again, you get the same thing we just showed. You get 2 oxophosphatanes, right? Where you have H and R on the same, or methyl and R on the same side, or methyl and R on opposite sides. Right? Again, this one's favored, and that leads to trans double bonds. So this doesn't really explain our selectivity, right? Why with the cycloaddition that, right, you're going to want to arrange your groups to come together so that the R group and the methyl group are on opposite sides, right? And again, if that's how it worked, you would get trans double bonds as your product. So there's another mechanism that's, of course, the more complicated one. Nothing's ever easy for you guys. Right? And it is called like the puckered pathway, the puckered cycloaddition. So I'll show you it, and then I'll try to draw it. Where instead of the Wittig reagent, the ylide, and the aldehyde or ketone kind of lining up parallel to each other and coming together like this, they line up turned. They're like 90 degrees from each other, and that minimizes the interactions between their functional group or between their alkyl groups, and then that leads to a cis orientation of the groups. So you can see that you have in the first structure, you have the ylide and the aldehyde basically at 90 degrees from each other. They're basically orthogonal. They do the cycloaddition, they stick together. And then the second structure, you can see, it's hard to see maybe, but the R group and R1, they're both pointing down. They're on the same side, right here and here. They're on the same side of that forward ring. They're both down, right? And then that leads to the cis double bond, right? If you try to flip it around, where you put the 2 R groups on opposite sides, the triphenylphosphine, that large phenyl group on the phosphorus, bangs into the R group and destabilizes that transition state and leads to a less stable oxaphosphatane. So that lines up with this mechanism, lines up with, right? We always get cis, right? When you make the group on the aldehyde bigger, more cis. When you make the groups on the phosphorus smaller, less cis, right? It doesn't touch the stabilized iolide, but don't worry about it. Right? But so if you look at this transition state, right? If the group if R1, the group on the aldehyde is big, right? It wants to orient itself more away from the phosphorus, right? So that transition state explains why when you put two bigger groups on the aldehyde, you get more Z, right? Because it's harder for that aldehyde to flip over. And when you make the groups on the phosphorus smaller, it makes it easier for that second transition state where the R group is closer to the phosphorus to happen. So this puckered mechanism kind of explains all of the observations of the Wittig reaction. So it's a 2 + 2, but it's like turned 90 degrees. So, that all make sense? Seem reasonable? Can you kind of see it? All right. Are you just lying to me so I don't like talk to you more? Okay. So, just making sure. There's only 2 of you. It's a safe space. Okay, that's good. And Zoom knows I just talk directly into my ear, so like it's a safe space for them too. There's 9 of them, or whatever, 7. So some Wittig generalizations. The reactions go through an early transition state. Right, so the interactions that you see when the 2 groups come together are the interactions that matter, right? So it's not the interactions that you see in the product, it's the interactions as the 2 starting materials come together, right? So it's an early transition state, right? So how the sterics of how those approach is what's going to dictate the selectivity in the reaction. How stable the oxaphosphatane is doesn't matter. The oxaphosphatane that you end up making, the one that is preferred in the reaction, is actually less stable because it has the 2 R groups on the same side. Right, so let's go back for a second. Right, you'd rather have the bottom oxaphosphatane, right? Because those 2 groups are far apart. But you make the less stable oxaphosphatane where the 2 R groups are together because it's easier for the aldehyde and the Wittig reagent to react in the way that it's shown on top. So it's not looking at how stable the 4-membered ring is, it's looking at how easy it is to bring the 2 groups together. Right? So the puckered transition state, the one where they're at 90 degrees, is favored over when they just come together and are planar. Right? So that is why you get the Z selectivity. That's why you always make cis double bonds. I'm going through too many slides. I don't want to spend this weekend making slides. I don't want to. No more. No mas. All right. Clicking over now. So the highest Z selectivity is when the interactions in the puckered transition state, the 1,3 interactions, are largest. So right? So I can do this. So right, you've got your this, and then you have your O. Right, so this is that 1-3 interaction. So larger R groups lead to bigger 1-3 interactions, which favors flipping it over. Right, you want to move that R group away from the phosphorus, and then this leads to more Z double bonds. See, like I just realized we're going to talk about something that I've not ever talked about before with you guys, and I would have talked about it as I started the semester. So figure it out. This is a good diversion, so I don't have to actually like make more slides. But I don't know the numbers though. So, right, so bigger R groups, more branching leads to more Z. And then replacing the phenyl group on the phosphorus with an ethyl group reduces the A1-3 interaction, the 1-3 interaction, and then leads to more, and reduces the Z selectivity. So on here, I have something that I have like A value, right? I have like the phenyl group has an A value of 2.7 kcals per mole, and an ethyl group has an A value of 1.8 kcals per mole. This is like a rough estimate of size that is used, and and it's basically based on cyclohexanes. So say you have phenyl. And everyone has to get this next question I'm going to ask right. Because they're teaching this right now in Organic 1. Which one's more stable, A or B? No. A. Right? Axial's bad. Right? This is favored. The A value of 2.7 kcals per mole. So that is the energy difference between A and B. So this is plus 2.7 kcals per mole. So this is 2.7 kilocalories per mole less stable than A. Right? So we can use that as like a rough judge of size. Right? Because what's destabilizing B compared to A is the interaction of that phenyl group with these hydrogens, right? So you have the A1-3 interactions here and here, right? So the bigger the group, the more A1-3 interactions. So you can say, oh, the A value is a rough measurement of size. The difference between A and B is determined by how big the group is that's axial. And this is a number I think I remember, I'm not 100% sure. I do believe it is 1.56 kilocalories per mole is the number to get a 10-to-1 ratio of something. So 2.7 kcals per mole is somewhere around, probably like 15 or 16 to 1. So you have like 16 of this to every one of these. right? When I go to ethyl, that number goes to 1.8 kilocalories per mole. So it's closer to like 10 or 11 to 1. So it's significantly smaller, right? I think tert-butyl is like 4. And you just never see tert-butyl axial. Ooh, tert-butyl axial. I know it's scary. Someone just shivered. They're like, ooh, tert-butyl axial. Doesn't even say it, man. Right. So when you see A value, that is like kind of a measure of size because the bigger the group, the bigger the A value. So when you compare, right, so we're basically just comparing size here, right? So we're saying, hey, phenyl groups are bigger, like you can kind of just see that, but here's a numerical value for size. It's about 50% bigger. And so that leads to more Z double bonds as compared to when I put a smaller group like an ethyl there, that leads to more E double bonds. And then the stabilized ylide reacts through a later transition state. So that means it wants to make the most stable oxaphosphatane it can, right? So unstabilized ylides react through early transition states. How do these two things fit together better? Stabilized ylides react through late transition states. Which of the two products, in this case the oxaphosphatanes, am I going to make that is most stable? So it makes the oxaphosphatanes that leads to the trans double bond because it goes through a later transition state. So adding that electron withdrawing group doesn't change how the transition state works, but it changes the transition state's energy. It makes it closer to the energy of the oxaphosphate. So going back, right? So stabilized ylides favor this because the unstabilized ylides are comparing these two things. They're comparing which of these transition states is more stable. And it's like, well, this one's more stable because the R group is away from the big phenyl groups. The stabilized ylides are comparing which of the two oxaphosphatanes are more stable because they're going through a late transition state that looks more like the oxaphosphate. And this one is more stable because the two R groups are far apart. There is still this interaction here, which isn't great, but you have your two R groups further apart, and that makes that more stable. So by adding that electron withdrawing group, you're changing what stability you care about. You don't care about how stable the two things are when they come together. You care about how stable the product is that they form. And that changes your reaction. Right. Also, something about the stabilized ylide is that making your oxaphosphate might be reversible. Right? So you might make the less stable oxaphosphate and it might just go back and try again. So it's more under thermodynamic control, where it's not just like, however these go together, I'm good, kinetic control. This is, okay, these went together, this is pretty unstable, I want to go back and try again. All right. So selectivity from ylides derived from secondary halides is usually pretty low. Right? I have my example from my paper here where I got like a 2-to-1 mixture of E and Z because I was using it on a ketone. Right? So ketones and secondary halides don't give a lot of, like ylides derived from secondary halides. Does everyone remember where an ylide comes from? Right, so like I was just showing you ylides, but ylides come from, you usually have an alkyl halide, right? And phosphorus has a lone pair, just like nitrogen. And it will attack the carbon that has the phosphorus and kick that off. Or attack the carbon that has the halide, I'm sorry, kick it off. And you make X phosphorus plus, and then it has a salt. So this is oftentimes how you buy Wittig reagents. You buy them as this salt, the phosphonium X salt, and then you add a base, I'm going to have generic base here, B, is going to come in, grab the hydrogen, and make the ylide and make the conjugate acid of the base, right? So if you're making an ylide from a secondary halide, so an ylide that has two groups on it, so if you have right, so that came from triphenylphosphine and a halide and a secondary halide. These don't give you good EZ selectivity. Same with ketones. They don't give you good EZ selectivity. You get good EZ selectivity in aldehydes. And that makes sense if you think about the transition state, because when you have an aldehyde, you're differentiating the size of a hydrogen and a carbon chain. And there's a really big difference in size between a hydrogen and a carbon. If you have a hydrogen, if you're comparing a methyl to an ethyl on a ketone, there's a size difference, but it's not huge. It's not as big as the size difference between a hydrogen and a carbon. So you get less selectivity because there's not as big a size difference. Right, and that's illustrated here. Right now, of course, yes, I know Zoom, you're mad at me. I somehow missed this protecting group on every one of these. So let me fix this real quick. That's better. So I'm not going to go through like every single step of the discodermalide syntheses. That seems like sort of looking for a lot. Right, these are like usually between 25 and like 40 step syntheses. I want to go through a few steps that you guys, some of them you already know from Organic 1 or Organic 2. And some are new reactions or like variations of vinegar reactions that I want you to see. And then also kind of build on stuff we've already seen in class thus far. So this is synthesis from James Panik, who was at Boston University when he did this. I don't know if he's still there or not. But this is just the steps for the section of discodermalide I have highlighted in yellow here. Right, so just this, it's like C7 to C14. So if you start counting 1, should you be able to see the slides? Of course. Way to suck me. Way to go. Thanks, Jenna. Let me, for whatever reason, have to jump through this hoop to get to this. There we go. Aha. There we go. Okay. So, discodermalide, there you go. Everyone can see it now. We did it. And so, the yellow fragment is the C7 to C14 fragment, I do believe. So if you start counting at this carbon, it's 1, 2, 3, 4, 5, 6. And that first yellow carbon is C7. Right? So, the first step here, you guys kind of know this, right? Step 1 is putting on a TBS protecting group. In Organic 2, we talked about TBS protecting groups as being put on with TBS chloride, right? TBS triflate, triflate's just a better leaving group than chloride. It makes it so it's easier to put that silicon group on the oxygen because it has a better leading group on it. And then 2,6-lutein is just a base. So when we did these before, we used triethylamine, pyridine, imidazole, and maybe DMAP. 2,6-lutein is just a different amine base. And then, does everyone remember what this is? O3 and dimethyl sulfide. We were all literally there in Organic 2. We bonded over ozonolysis with a reductive workup, right? So this cleaves this double bond and makes an aldehyde. And there's a minute left, and I want to go over the mechanism of the Corey-Fuchs reaction, which is this guy right here, which is a Wittig reaction followed by a lithium-halogen exchange. So we will save that first. Everything good, Zoom? Thank you, guys. I got a big thumbs up from Jonah. So we're good. See you guys. Hey, Alexis. You too. Is Alexis still here? She is. Hey, Alexis. That's fine. Are you going to be in person for lab still, or are you going to go online for both? Okay, I just want to make sure. Cool. Thank you. Okay. Bye.